So today, okay, so good morning. So today we will move on. Last time we did, only motion in one dimension. And this time we will go to higher dimensions and, the Jacobian matrix with all things which I said formally, we'll look at it in some detail. Okay. So let me check my settings. Okay. So I just want to discuss, our motion in one dimension with some more details. So let x0 be an extremum of the potential V of x. Okay, that means dV by dx. So this implies that at x equal to x0. Okay, so what we can do is do a standard Taylor expansion. Okay, so V of x about x naught. So it will be V of x naught plus dV by dx evaluated at x equal to x naught, but that is 0, just as I wrote above. So the linear term drops out. So the first term that will come will be d square V by dx squared. Okay, and depending on the evaluated at x equal to x0. So the value of second derivative times x minus x naught whole square upon 2 factorial plus this is, you should read of order of. Okay, it's order, we are throwing away terms of order x minus x naught whole cube. This is a great symbol, by the way. So this is a definition of m omega square. I put plus and minus because depends on d square V by dx square at x equal to x naught can have both signs. It can be positive, it can be negative. So depending on that, I want omega to be real. Okay, so V naught plus half m omega square x minus x naught whole square plus order x minus x naught cube. So this is just the expansion. Okay, so our idea of a stable fixed point is that the plus sign works. So there will be harmonic. Okay, and minus sign if it's an unstable fixed point. This easily follows. So just sometimes it's easy to change variables to eta, which is this is just eta, the Greek symbol eta. So they define that to be x minus x naught, and throwing away this term, we can see that the equation for small enough eta, Newton's equation just becomes d square eta by dt square equal to minus or plus omega square eta square. Okay, so if it is plus here, it becomes minus. Is this correct? Okay, it should be linear in eta, not because it took one derivative. Okay, so that 2 is not there. Is that clear? So general solution is eta of t equal to a cos omega t plus b sin omega t if for the upper sign. Okay, and it is a e power omega t plus b e power minus omega t for unstable system. So we can see that at least for small values, if you check this thing, you can see that the sign matters, and so stability requires that this particular thing has, this term has this positive sign. Is this clear?
Yes, sir.
Okay, so now we'll do some simple games, and so now we look here and look at this potential. This is a random potential. I just drew something. Okay, so let's see here. So this thing has two fixed points, right? I mean two extrema, because dV by dx is 0 here. No, and 3 out here, one more. Okay, so we carry out 3 fits for one of the fixed points. So the idea here is that we got some approximate expansion about the fixed point. If we throw away all higher order pieces, let's see how well it works. So this is what I'm doing in the next. Okay, so you can see here that the curves in red are the quadratic approximation. So you can see that if you come close enough, the window which I'm showing, it's working very well, but if you go far enough, it's not working so well. Okay, so this is, but this is to be expected because we threw away terms which are relevant, and there is the blue curve. And by the way, I do have a comment about all these curves, etc., that you have that you're seeing. Generally, I actually do real curves. Okay, so v of x is some, I've forgotten what I chose, but I drew a graph with a given. I took some function and drew this. I think it might be quartic, is my guess, some quartic function, and I did this, and so these are all real fits. So whatever I've drawn are real. Okay, so this is something which I always do. It sometimes means a lot of work, but it doesn't matter. Okay, is this clear? So you can see that it works only well in the neighborhood of that. Okay, so one thing which I asked you to do is to check that it takes infinite time to reach a separatrix. So recall, if x0 is an unstable fixed point, then the point x0 and 0 in phase space is a separatrix. The energy E is V of x0. Okay. So let us consider phase trajectory with the same energy. The claim from last lecture is that it takes infinite time to reach a separatrix. The first thing you do is you change variable again, like before, to eta, which is x minus x0. Okay, and consider phase trajectory eta naught p at t equal to 0. So it is. So what we are doing is it's at eta naught, but that is so, and we assume that eta naught is small enough that our quadratic truncation works. Okay. So first point here is that at x equal to x0, so so eta equal to 0 is our location of the spatial location of this separatrix. So I'm choosing eta naught and p, and we assume that eta naught is small enough that our quadratic truncation works, and p is determined by the energy condition. So recall, what was the energy condition? E is V of x0 would be equal to half m. Okay, so p, right? So I'll change over to, so that will be p naught square upon 2n plus V or at eta naught. Okay, so the energy, so we are choosing, so this is E, right? Okay, so now, so the point here is we assume that eta naught is small enough that our quadratic truncation works, and P is determined by the energy. Okay, so now you can go back there and you can expand, this is bad. So you just go ahead, and if you, so what I'm saying here is that you will see that P naught, from this you can get an expression for P naught, and which you can write, and then you'll find that the solution, so this exercise, check this. Okay, eta of t will take some form of A e power omega t plus B e power minus omega t. Okay, so at t equal to 0, what we have is that eta of t is equal to eta naught. Okay, but in general, so these numbers p, and so I called it p naught here, but actually it should be p to be. Okay, so this is what we get, and the energy conditioning implies that p equal to plus or minus m omega naught eta naught, which we should choose the sign that pushes it towards the separatrix. And you can just check in this case if eta naught is positive. This happens for the negative sign. Thus what we see is eta of t is equal to eta naught e power minus omega t. Okay, so when will it reach the separatrix? When eta becomes 0, right? Eta equal to 0 is the location of the separatrix. So you can see that it takes infinite time. So we're just looking at a neighborhood. We have put it pretty close to it so that the approximation works. So we see that eta of t is equal to eta naught, which is at constant times e power minus omega t. Okay, and remember what is omega? Omega is the sign, is the second derivative, is determined by the second derivative at x naught. Okay, so you can see that t for eta of t will become 0 only at t equal to plus infinity. Okay, is this argument clear? So this argument doesn't, just me just go back. So it says that it's enough for me to look in this neighborhood where, the approximation is very, very good. So I can make I have freedom in choosing it or not. So you can say, what happens if it is further away? Eta naught is very, very small. Let's say it takes some, so let's say we take eta 1. So eta 1 it will take some time for it to take some finite amount of time, say from eta 1 to get to eta naught. And then once it reaches eta naught, this formula which we have written works, and that takes infinite time. So it's infinity plus some, whatever is the time it takes to go from eta 1 to eta naught, and so that is just still infinite. Okay. And you can see we have made no assumption about any property of the potential, details of the potential, except for the fact that x naught is an extremum, and the second derivative has a particular sign. That's it. Okay. Is this clear? Okay, so now we will move on to motion in 2 dimensions. Again, Newton's equations kind of stuff with conservative forces. So we'll choose Cartesian coordinates x, y, but generally I prefer to use x1 and x2 because we can use dummy indices I, which is run over 1 and 2. And let's consider forces, conservative forces. It's the force F is minus gradient of v of x. So there are 2 equations of motion, one for each coordinate, which you write in this fashion. Okay, again, the energy is a constant of motion, so you can do this. So here what you have to do is multiply by dxi by dt and sum over. And then you can integrate once again. It's the same thing. And E is determined by initial conditions. So this is just usual thing. This is kinetic energy plus potential energy equal to total energy. Okay. So in this simple case, this is true. We will see examples where this is not true. Okay. The phase space is now 4-dimensional. Why is that? Because we'll have x1, x2, p1, and p2. Right. So phase space is 4-dimensional. So now, so if you give me an initial condition, if you give me a value of energy, the phase trajectories are restricted to a 3-dimensional hyperspace of constant energy. So this is an equation. So replace x dot mx dot with p. So this gives an equation in phase space. One equation, so 1 degree, 4 becomes 3. Okay. Now fixed points are determined by the simultaneous set of equations. So we need dv by dxi should be 0, both for I equal to 1 and 2, in addition to the obvious pi equal to 0 condition. So now we need it to be a true exchange. So the first derivative along x and y should vanish. It's not enough for it to vanish along x or y alone. That won't be a fixed point. Okay, so now we will see how to handle the case of, higher dimensions. So the formula here actually hold for greater than even 2. But so let's just do this. So v of x. So let x not be a fixed point. So what does that mean? It means dv by dxi at x equal to x naught is 0. Okay. So as usual, and I just defined eta to be this thing. So v of x will be v of x naught plus this thing. But now you see here that because we have multiple directions, we'll have a derivative of matrices. Okay, so this is the matrix. Okay, this is clear, and it's a symmetric matrix. So it's what you're doing is di dj of v of x. So we'll call this hij. And this matrix is called the Hessian of the potential at x equal to x naught. And the stability is of this fixed point is determined by studying properties of this matrix. So for 2 dimensions, it will be 2 by 2 matrix. Okay, so I'll pause here for questions. No questions?
Sir, in HI, there will be 3 terms, del 2, del xi, del 2, del yi, and the mixed derivative.
Yeah. So for 2
3
dimensions,
terms.
yeah, the matrix H will be d1 square v, d1, d2 v, all evaluated at x naught. Right? That's what this matrix is. Okay. So here's the thing. So I'm showing you pictures. So what I'm plotting here is the following: is throwing away this piece and just taking the of course the linear piece is gone, and v of x naught is just a constant, so it will move it up or down. So that's not. I mean, so really, what one is doing is plotting this kind of thing. And what I'm showing you is something intuitively which is stable in all directions. So if you jiggle it along this direction or this direction, anyway, it will come back to the lowest point here. Okay. So this is stable. This is one possibility. Second possibility is totally unstable. Okay. And the third one is what we call a saddle point. So here you can see that in this direction, it's unstable, but in this direction, it is stable. Okay, stable in and you can see why it's called a saddle point. You know, have you seen this thing where people's horses, they put and sit on it, right? That has this shape, right? So that's called a saddle point. Okay. So are
in
these
one
pictures
direction
clear?
and in other, by direction you mean that from which direction we are approaching that point, that direction means if we
Yeah. So there are two. So if you pick a point, there is actually a 2-dimensional worth of directions, right? 2 angles. So which direction we have to specify? That's something which we will discuss next. Precisely, we have to do things. Okay. But the pictures is what I want you to remember. So there are 3 kinds of pictures. That's it. Okay. And no more. And we will see in a moment how that works. Okay. So how do we do the mathematics? Okay. So somebody actually asked 2 lectures ago, will you show the mathematics, etc. And so so this is something which we will see now. Okay. Again, you may see this in math physics. You may have already seen it. Some of you would have seen it in BSc itself. Okay. So even if you haven't seen it, it's fine. The Hessian is a real symmetric matrix. So Hij equal to Hai. Okay. Symmetric matrices are diagonalizable by special orthogonal matrices. This is a very important statement. Okay, so that means this matrix that I have can be written as O transpose DO, where O belongs to SOP. Let me be more general, it doesn't matter. SON, if it's n by n, we are doing only 2, so it is SOP. Okay, so, and where D is a diagonal matrix. So D is diagonal matrix. Okay, so D is a diagonal matrix. So what we will do now is we'll define a new set of coordinates. So remember we did eta. What was eta? Eta was x minus x naught. Okay, these are vectors, 2-dimensional vectors. But I show it as boldface here. So you define a new coordinates xi, which is O acting on eta. O is a 2 by 2 matrix, so it will give me. So now, if you look at, go back and look at this term, V of x. It's just h acting. So you can see that this term can be written as follows. It can be written as theta 1, theta 2, h. Okay, so that's what I'm writing, the short form for writing that. Okay, so what you find is that once you do this thing and you substitute h, which is O transpose D, this thing, and eta transpose is just converting eta, which is a column vector, into a row vector. So it's just that. And you will see that this combination here becomes xi, and this combination here becomes xi transpose. Okay, so these xi's are nice variables. Okay, so then in terms of that, we'll get to d1 xi1 square plus d2 xi2 square. So it sort of separates out. So these xi's have a name. We'll call them normal coordinates. Okay, and the key point here is they depend on the point x0. If x1 is some other fixed point, there you have to go locally again. There you have to compute the Hessian of the matrix of the potential at that point, and then there will be a different orthogonal matrix and different set of norms. So these are normal coordinates at or near x equal to x0. Okay, now I can be more specific. So we get these numbers d1 and d2, and the kinetic energy is just usual. You can go back and check that it is just m xi dot square upon 2. Okay, in xi coordinates we thus have 2 decoupled. This is the most important point. 1d problems. Of course, after we throw away all the cubic and higher order pieces. So now stability is very simple. It just says that if both d1 and d2 are greater than 0, we call it stable. If d1 is less than 0 and d2 is less than 0, this is unstable. But if one of them is positive and one of them is negative, so if you take, let's look at this guy. If d1 is greater than 0 and d2 is less than 0, what it means is that d1 along the xi1 direction, that is, if you go, it will be stable. But if you go along xi2 direction, it will be unstable. So that's the saddle. The second one is where the roles of xi1 and xi2 get exchanged. Okay, is this clear?
Stable means along any direction it is stable. Any direction of motion.
Yeah. So you can take, see, it's decoupled. So if it is, so you can always break up. If you, let's say we did something which is not, so you can actually prove that xi1 and xi2 will be orthogonal directions. Okay, but so what will happen is that if you have some direction which is neither xi1 nor xi2, and at some angle, you can rewrite that as a linear combination of xi1 and xi2. These are like vectors, right? So you can write them as some linear combination of these two directions, and then you can see, again it will decouple because we're working only to first order, and so you can still say what will happen. Okay, but the operative thing is that there is in saddle point there's one direction which is stable and one direction which is unstable. Okay, so going back to this picture, so this would be either, let's take the third example. So let's say this is xi1 and this is xi2. Okay, but of course you can go in some direction like this. Nobody says you can't. Okay, but this can be written as sum of vectors along these two directions. So you can create unit vectors along xi1 and xi2, and that will provide a basis for arbitrary vectors. Okay. I'll pause here. Any questions?
Sir, could you please explain how the signs of D1 and D2 determine the stability or instability?
It's 1D problem, so you can ask the same question here in 1D. So in terms of xi1 and xi2, so D1 is like m omega square, like here. Take xi1 if you want. Okay, so d1, if it is positive, so d1 is like m, so d is like, so d1 will be like m plus omega square. So if it is positive, just like here, right? You can ask the same question here, right? Plus means it is, so you have to look, or even better look at this equation of motion. You know that, minus sign means it's a restoring force, right? So that's
yes,
the
sir.
stable case. So that's the one. So it says if this is plus, this will be minus. Okay.
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 Hmm.
So,
Yes.
I mean, the advantage of whatever by going to normal coordinates is that they decouple and it becomes, there's no mixing, at least to this order. I mean, a higher order they can mix. Okay. But we are only looking very, very close where this approximation is good. Okay. So that's actually a very good question. So what I'm saying here is that if you look here, that everything decouples. So yeah, so this is the key. Kinetic energy, of course, you have to check this. Kinetic energy is also, so you will get half m is a kinetic energy. Okay, even that decouples. So you can see that you can just write the total energy as set of these two guys. Okay.
Okay, sir.
So I'm just I'm able to borrow results from 1D. Okay. So what about neutral equilibrium? Even that is possible. So I'm giving you an example. So a neutral thing would be, for instance, here is an example where D1 is greater than 0 and D2 is equal to 0. Okay, so this has fixed points 0, 0, which is here, like top of this thing. But then it has a whole bunch of fixed points, which is a circle. It's a different color. Okay, take that to be a circle, this circle. Okay, and these are neutral. Why is that neutral? Because it is stable in this direction, okay, because D1 is greater than 0. But then along this direction, if you kick it, it will just roll and stay there. I mean, it will just be there. Okay, so you have a set of infinite set of, so this is a set of fixed points. Okay, so neutral equilibrium is also possible. Okay, so here I was.
So this last set where basically you're saying about the stability depending on the direction that we are choosing, right?
Yeah. So so the correct statement here would be along Xi1 it is stable and it is neutral along Xi2. So
Okay.
So let's, for instance, pick a point here. So if you push it, so the tangent will be, or to that circle will be like this. Okay, so that would be Xi2 direction here, and this would be Xi1. Okay. So this is also, so in 2 dimensions you can see that it gets richer and there is some structure. Okay. So now when you go to higher dimensions, you can have, we just looked at took some arbitrary potential and I said there is only one constant of motion, but it is possible to have additional constants of motion. Okay. So let me introduce plane polar coordinates as follows, standard thing. From rho is square root of x squared plus y squared, and phi is just tan inverse of y by x, or if you want tan y or tan phi. Okay, and rho takes value from 0 to infinity, and phi goes from it's a variable 0 to 2 pi. I don't include 2 pi because 2 pi is identified with 0. Okay, and the inverse of this is just x equal to rho cos phi and y equal to rho sin phi. Yeah, so one thing which you should learn to appreciate is the difference. There are 2 kinds of Greek phi's. Okay, and in physics, we differentiate between these 2 guys. Okay, so if you know LaTeX, this is called regular phi. This is called a variant of phi. If you don't know, it doesn't matter. Okay. So then you can work out T. T is a symbol which you use quite often for kinetic energy. It's half mv square, and if you work it out, it just becomes, in terms of just change variables from x and y. And so you can take this workout. So if you look at this, x dot will be rho dot cos phi minus rho sin phi dot. Right? So you can plug all those things into that, into half mv square, and get this thing. So now comes the key point, is that if we can show that Newton's equations, there will be two equations, but the two equations here become m rho double dot plus m rho phi dot square should be minus dv by d rho. And similarly, d by dt of m rho square phi dot should be minus dv by dt. So this is just Newton's equation. So this is just an exercise for you. Now comes the interesting thing. Suppose the potential is independent of the coordinate phi. Then what does that mean? Partial derivative of v with respect to phi equal to 0. And that implies that d by dt of m rho square phi dot is 0. What does that mean? M rho square phi dot is a constant of motion. Okay, so energy, of course, total energy, T plus V is a constant of motion, but we get a second constant of motion. Okay, but this requires some special, it doesn't happen for arbitrary potentials. Okay, for arbitrary potentials, this equations will be used, and you may not have a constant. Okay, what is this conserved quantity? You can go back and verify that this is nothing but the angular momentum. Remember, in 2 dimensions, there's only one component of angular momentum, which I write as x1 p2 minus x2 p1, and exercise show that L equal to m rho square phi dot. Okay, so the potential being independent of phi implies that all directions in the plane are the same. So there's isotropy about the origin. If you are at the origin and you look, all directions look the same. And of course, the energy is given by this. It's just T plus V. T we have written here. I just put that here. Plus V should be the energy. But now comes the interesting thing, that if you see here, we can trade phi dot for L. So okay, so we can. This implies phi dot L is a constant of motion like E. Okay, so if you go there and so replace every occurrence of phi dot, so phi dot square will be square of this thing. So you will see that this becomes, so what we get is that now when we express trade phi dot for terms of L, so what we get is half m rho dot square, which is there, but this term now becomes just some function of rho, L square upon m rho square plus V of rho. Okay, so this now looks like a one-dimensional potential. So we call it an effective, it's a motion in 2 dimensions for sure. Okay, but what I'm saying here is that this looks like we can write an effective potential which depends on L. Okay, so E and L are constants of motion, and you have to give me those numbers from the initial. Okay, so this is something, it appears that we get a one-dimensional problem for rho with effective potential depending on the initial conditions through L. But important points to remember here is that rho is a positive object. It cannot go to, let's say it's not negative. It cannot become negative. Okay, but that's okay. So that we have to remember. So now we can actually integrate these equations of motion. Okay, like we did before. So we can solve for rho of t like we did in the one-dimensional case, keeping in mind, of course, I just mentioned this. So again, rho dot will be plus or minus 2 minus E minus V effective of rho upon N. But there is something very interesting. What happens at rho equal to 0 is that L square upon rho square tends to infinity when L is non-zero. Thus, in this case, rho cannot be 0 at all times because it's like a barrier. You need to have infinite energy to go to rho equal to 0, and that's not possible. You can't. Okay. So suppose we are able to integrate this thing, then we have determined rho of t. Now we can, so the advantage of this, so if we solve this differential equation, we get rho of t. Now we can go back and look at for this equation, phi dot was L upon m rho square, but we already know rho square, so we get phi dot equal to some known function of t, and so you can actually integrate. Okay. But now the trajectory of the particle will be, so if the particle is moving, so you could write a trajectory as some rho as a function of phi. So that would require you to do d rho by d phi. So what you can do is a very nice trick, which says that d rho by d phi is equal to rho dot by phi dot. Okay, so we know rho dot, we know phi dot. So you take the ratio of these two guys, and lo and behold, you get this equation. I'm not saying for arbitrary v we can do this integration, but in some cases we can. Okay, but we might be able to do it numerically always. Okay, so this is the way we can. So once you have extra conserved quantities, life becomes easier. Okay, so in 1D we saw energy being conserved told us that we needed to solve only integrate first order differential equations. And it's an important point that first order differential equations are easier to solve than first or second order, obviously. So here also what happened is that we somehow got two constants of motion, and we could use those things and go backwards and solve for so we only solve integrate first order equation. Okay, so this so finding constants of motion, different color. Helps simplify things. Okay, so we will come back to this, and there's another beautiful point here is that sorry, yeah. So this, the fact that it's independent of some coordinate actually means that there is a symmetry in the problem. So there is a theorem due to Noether which connects symmetries to conserved to constants of motion, if you wish. Okay, and this is something which we will study later on in this course, but this is really one of the first examples. And so you can ask, if we are given some general dynamical system or a Hamiltonian, this kind of system, how many constants can we find, etc., etc. And these are things which we will discuss in some detail as this course proceeds. But today was just to show you how we go about handling situations in higher dimensions. I just used 2 dimensions. So you can ask, suppose I have it to 3 dimensions. So yeah, so if you go to 3 dimensions, so we can come back to again this sort of story. Like I said, this here we assumed only 2, but you can see I can go to any number of dimensions and it will still go through. And so we'll accept the analog of D will be some diagonal matrix with the n entries. Okay, so you can see there'll be much so there. So you will get something like diagonal matrix D1 to Dn, and so you can see that there'll be many each of these things can be greater than 0. They can be less than 0, they can be equal to 0. So you will have 3 power n possibilities. Okay, so but for stability, D1, D2, D3, D4 up to Dn, all of them should be positive. That is something which you can say. So that is one extreme case that requires all of them to this thing. Neutral will let you have a few more zeros. So neutral will let you put some zeros in the story. So I think I'm done for today, and so I'll pause for questions, comments.
sir.
Yeah.
So the part where you have written eta transpose into H into eta, can you explain that once again?
Yeah. So eta transpose H eta, that is the quadratic piece. That you agree, right? This term you understand, no?
I was asking about this term itself, why we have done.
That is this term, no? That is this term. I've written in matrix form, right? So this is eta transpose. This is eta. So eta transpose. H is a 2 by 2 matrix. Eta. That is this term. This whole term is that.
Yeah, okay, so I got it.
Hmm?
Thank you.
If you expand this, and it's just algebra to show that these two are the same.
Yeah.
So once we have that thing, then you just use xi is O times eta, and xi transpose, O is O dot eta transpose, which is the same as flipping. So if you have matrix A and B, AB transpose is B transpose A transpose. Okay, this is just a formula from matrices that you should know, or you can check. And once you do that thing, you find that it fits naturally in terms of that. Okay.
So in two dimension we have done, we only have two constant of motions, or are there any other possible cases also?
Mm-hmm. Yeah. So there are some technicalities, but there is a sense in which if you have a phase space which is 2n dimensional, you can have n, maximum you can have is n constants of motion in involution. We have to define that with each other. Okay, so in 2D, in that sense, there are exactly two. Okay, but there can be other, if you give up this involution thing, you can get up to 2n minus 1. Those are called super integrability. So systems for which we can find, n constants of motion, they are called integrable. Okay. And then those which don't are called non-integrable. Generically, systems will be non-integrable. So in 6 dimensions, so if you take 3 dimensions, for instance, a Kepler problem, which is like a planet moving around the sun, etc. In that problem, it is in space. So you will have 3 plus 3. Phase space will be 6 dimensional, and so you will have 3 constants of motion. And it turns out that you can get there are many constants of motion I can write, but this involution condition will reduce it to 3. So angular momentum will be conserved because, okay, and the symmetry will be rotations. We'll see all these things. Okay. So finding integrable models in higher dimensions, these are all complicated. Interesting problems, and people have studied a lot of it. But most problems which we'll face in real life are not necessarily integrable, or they might be partially integrable. So you may find, you may have a 3-dimensional problem where you'll have 2 constants of motion. So that still helps. It makes the problem simpler in some ways. So you can trade at least instead of solving 3 second-order coupled differential equations, you may have to solve only maybe 2 first-order and 1 second-order. So these kind of things happen. Okay. Any other questions? So there are some small exercises here. For instance, I just this particular exercise I have in mind. Yeah, this one. I strongly recommend that you do this. I think you will learn a lot about what we are trying to do. Okay? So this is something strongly recommended. Okay. So I think I will stop sharing. Go ahead.
Sir,
Yeah,
sir,
go ahead.
I forgot to give attendance, so
So say
in
present
last
now. Say present now. I'm not going to lose sleep over that.
Okay, sir.
I'm stopping recording.